Dude, it's a great day today. I got math and then contact canceling.
Also don't like soda.
All right. You guys ready? So actually remember to hand out the attendance sheet today. There we go. I will begin with a word of prayer. So, dear, dear Heavenly Father, we thank you for this day and for this class. I have just pray that you'd be with us, help us to glorify you in what we do, and just to understand polar coordinates. Lord, in your name I pray, Lord Jesus. Amen. Polar coordinates, yep. So, let's see here. Nope, it's not here. I still have a thing to give back to somebody, but they're not here, so. All right. Oh, I guess I'm supposed to do that thing, right?
Very on it.
Come on, computer.
Surprising. You falling to the way to the top hat? Hopefully for us.
Well. I feel like Top Hat doesn't have long to live here. You know?
Here as in Liberty?
As in Liberty, yeah.
What makes you say that?
I just feel like it's on its way out. Let's see here.
I might be able to.
Oh, they're renegotiating their contract?
Which means that we will either have top hat next year for cheaper, more
I hope-
expensive, or not at all.
Well, I hope they get greedy.
Who?
Top Hat, yeah. Well, if they get greedy, then they'll boot them. See, I mean, they might figure out that we could just be taking attendance with Canvas since it's like a built-in feature. But anyway, 4268. Apparently, Canvas has like, I've been told by some other faculty who cares infinitely more about these things than I do, which wouldn't be hard. Okay, so polar coordinates. What are polar coordinates? They're cool. All right, so here's the basic picture. If you pick a point like here, let's say, you could label that point x comma y, right? But you could also label it r cosine theta, r sine theta, right? Supposing what angle, how are we measuring that angle there? Well, it's the same one I introduced to you guys a while ago, namely the, you know, let's see here, what's the angle we're talking about? It's the standard angle, right? At least that's one choice for theta, I should say. The standard choice. So theta is measured counterclockwise from the positive x-axis, right? So if I, you know, wanted to give you formulas, here, what are the formulas? X equals to r cosine theta, y equals to r sine theta, right? I think it's useful to just stop here and graph sine and cosine. What does a graph of sine and cosine look like? So sine looks something like this, right? What's cosine look like? This, yeah, the same thing just shifted is a good answer. So it starts at 1, right? And where cosine is, where sine is 1, cosine 0. Where sine is 0, cosine is either plus or minus 1, right? And vice versa. So they're complementary in that regard. So if you do something like that, All right, so what I'm looking at here, right, is y equals, not y, excuse me. Well, let me just say that this is cosine theta. I don't really want to say y equals cosine theta. That would not be helpful. And here's the graph of sine theta, all right, versus theta, and I'm deliberately not giving a label to that axis, all right? My point to you is just this, is that sine and cosine, right, they're deliberately constructed. So first of all, I mean, just defining sine and cosine, how do you first define sine and cosine? Do you guys remember? What's the first thing we do? I mean, I hope the first thing you did in your mathematical journey was look at right triangles, right? And you looked at right triangles. In that right triangle, the hypotenuse is r. Down here, you've got r cosine theta, right? Here you've got r sine theta because sine theta is opposite over hypotenuse, whereas cosine theta is adjacent over hypotenuse. And so you get these formulas, right? But right triangle trigonometry only applies where? Right triangles, right? But also 0 to 90 degrees for theta, right? Past that point, you're really outside the realm of right triangle trigonometry. And yet these formulas make sense everywhere, right? These formulas automatically build in the plus or minus necessary to get you to quadrants what? So here's quadrant 1. Here's quadrant 2, right? Here's quadrant 3. Here's quadrant 4, right? And those correspondingly over here, we're talking about quadrant 1. And here we're talking about what? Quadrant 2. And here we're talking about what? Quadrant 3. And then over here, quadrant 4. So you notice that the sign, like plus or minus of sine and cosine, have been specifically designed, if you will, to make these formulas make sense in every quadrant, right? Like in quadrant 2, you have x less than 0, y greater than 0, which is what? That's how cosine is less than 0, sine is greater than 0 there, right? In quadrant 3, they're both negative. As you can see, this is where both the sine and cosine graphs are negative. In quadrant 4, you've got sine is negative, but cosine is positive, which is exactly what you want, all right? I think we take this for granted, but this is important to know about. And knowing the graph of sine and cosine is like very useful if you're trying to actually solve specific problems, right? Like for example, if you try to solve cosine of theta equals to a half, right? What's the calculator going to tell you? The calculator is going to tell you, 60 degrees or pi over 3, right? So the calculator is going to give you this solution right here. But there's another solution, right? Over here. And then there's there's two infinite families of them, right? So unless you know, at least in my opinion, unless you know about the graphs of sine and cosine, it's awful easy to miss solutions when you're solving sine or cosine equations, right? So point of order, like the first thing I would do if I were you, if I'm rusty on graph of sine or cosine, I would make sure I know those. I would take ownership of those going forward. It'll save you trouble. All right, this has been your pre-calculus refresher. Let me stop this. Now, so there's some annoying things here, right? Example 1. Given P, and I'll keep it pretty simple here. Let's say 1, 1, right? So those are the Cartesian coordinates. Can we find the polar coordinates for that? So we have what? We've got 1 is equal to r cosine theta. We've got 1 is equal to r sine theta. So you have to solve those equations. I regret my life choices in this minute. So let's go back here and do one other thing. Can you take these? And what can you do? You can solve these, right? So you can get, on the one hand, you can get that the tangent of theta is equal to y over x, right, by dividing these two equations, right? And we also, if we do what? We can also see that x squared plus y squared equals to what? If we square this and add them, what happens? You get cosine squared plus sine squared, which is 1, right? So x squared plus y squared is r squared. So these are sort of inverse relations. They're not quite inverse, but and of course the top one is for what? There's strings attached there, right? For x not equal to 0. The left equations, these are generally true, all right? Like there's no strings attached to the x equals r cosine theta, y equals r sine theta. Those equations are true for the whole plane. The x squared plus y squared equals r squared, and well, the y over x equals tangent theta, and to a lesser extent, x squared plus y squared equals r squared. There's some nuance there. Okay, but let's get to it. So r is equal to what? We could use the square root of 1 squared plus 1 squared, right? Because if we take the square root of that, we get what? R is equal to what? Technically, plus or minus, isn't it? You see that? You could go plus or minus here. I traditionally just say plus, all right? Unfortunately, well, anyway, let's one thing at a time. So the square root of 2 is r. What's my angle? Inverse tangent of 1. All right, so theta, how did you get that?
Theta is rather x minus x equal to 1.
Mm-hmm.
So just take the inverse of both sides and tangent.
Right. So you're basically saying you took this equation here, right, and took the next step and said, well, theta is inverse tangent of y over x. And that is sometimes true, right? Okay, so let's this be example 1. Leave yourself some space, all right? Example 2, suppose we have the point Q equals to minus 1, 2, all right? Then r is the square root of minus 1 squared plus 4, which is the square root of 5. And I guess I really should have drawn a picture over here to be sure, right? So our point was here, right? So it made sense that we had pi over 4, right? Geometrically, makes sense, yeah. Or AKA 45 degrees, yeah. So let's see here. This is 0, pi over 2, pi, 3 pi over 2, 2 pi. Yeah. If I draw a picture here, where am I? Minus 1 over 1 up 2, right? Like here-ish. So the angle I'm looking for is this angle here, right? So I need to find a standard angle between pi over 2 and pi, or if you like, between 90 and 180, right? How should I find that? So if you said add pi to inverse tangent. All right, so yeah, if we take inverse tangent of 2 over minus 1, right? What do we get? Inverse tangent of 2. Well, minus the inverse tangent of 2, actually. Inverse tangent's odd. You can pull the minus out of it. What is inverse tangent of 2? If you feel like we've covered this before, you should feel that way. This is the same math as finding the angle for two-dimensional vectors, right? We talked about this before, right? So 63, okay, so minus 63.4, I'll take it. And, all right, great. So that's obviously wrong because that would be down here, right? Like this down here is minus 63.4 degrees, right? Down here. So to fix that, the theta that we're wanting here is what? 180 degrees added to that, right? So you're looking at about, what, 117.6, is that right? A 1/16, I can't do math. Oh, good grief. Sad, sad, sad. All right, great. Now, here's the bad news. There are other choices. Okay, so like, let me call what I've done so far, let's say R1 and theta 1, all right, for these. All right. So for this example, I could also do, I could also put R2 equal to the square root of 2, and I could use theta 2 equal to what? Let me be very, very generic. I could take pi over 4, right? Plus 2 pi j. And this is for j in the integers, right? Any multiple plus or minus of 2 pi, integer multiple of 2 pi, same geometric, right? Same geometric point. Why is that? Try it out, right? X equals to R2 cosine theta 2. Y equals R2 sine theta 2. How's that work? Square root of 2, square root of 2, cosine of what? Pi over 4, plus 2 pi j, sine of pi over 4, plus 2 pi j. What happens to this extra piece? Well, sine and cosine are 2 pi periodic, right? So they just gobble those up. They're gone. What are you left with? Cosine pi over 4, sine pi over 4. That's 1 over root 2, right? So no matter what our choice of angle here, we still get 1, 1. It still works, right? So that's the one thing you can do. You can keep a positive radius, and you can add any multiple of 2 pi times the radian, or multiple of 360 if you're using degrees, right? Or multiple of 400 if you're using grads. No one uses grads, right? It's 400 grads, it's 360 degrees. You ever heard of this? Yeah, right angle's 100 grads. Yeah, no one knows about this, and that's fine. I'm sure the ancient Babylonians probably had another way to do it, but they're dead. Anyway, so they had their 70 years. But sorry, we're in Jeremiah right now. But here's the weirder thing. Check this out. I can also put R3 equal to minus the square root of 2, and theta 2 equals to pi plus pi over 4. So like 5 pi over 4. In other words, so I can make a negative radius, and I can shift the angle by 180 degrees. If I put those into the polar coordinate formulas, they still will give me back 1, 1. Try it out. X equals to minus the square root of 2, cosine of 5 pi over 4. Y equals to minus the square root of 2, sine of 5 pi over 4. We'll still get 1 and 1, because the cosine and sine, where's 5 pi over 4? It's right here. Cosine and sine are both negative there. In fact, the point we're talking about is the crossing point where they're both equal to 1 over root 2. There's so much information in these graphs if you can graph them carefully. So much information right at your fingertips. So there's that. So my example 2, we can also take this, 116.6 degrees and add any multiple of 360 to it you like. All right? Let me focus on the weird part. You can also say R2. Let me say it this way. If I say R2 is equal to minus the square root of 5, what is the polar angle I have to give for that to describe the same geometric point? Right, negative 63.4, exactly. It's the inverse tangent that we didn't use. Well, we had to modify it, right, by adding 180. So take it away, there you're back. And you can work it out. Indeed, again, x equals to minus the square root of 5, cosine of minus 63.4, and y equals to minus the square root of 5 times the sine of minus 63.4. We will get, just like we want, minus 1 and 2. So this is a theorem, right? Polar. So polar. Let's say I need some language here. A point P can be described with polar coordinates r theta. Say if, I'm missing an if here. If point P can be described with polar coordinates r theta, then we also have equivalent polar descriptions of number one r and theta plus any so number one, you can just shift the angle by any multiple of 2 pi. All right, that's one thing you can do. And number two, you can use minus r instead for your radius. All right, and your angle, you can do theta plus. Well, I mean, the thing is, if I can do minus 63.4. I can also do minus 63.4 plus any multiple of 360. That also works. There's infinitely many choices here for negative radius, just the same. So I got to think about this for a second here. I think I want, oh goodness gracious. Golly, I'll just say it this way. Plus pi, I'm being, kind of lazy here. There's probably another way to write that. But anyway, pi plus 2 pi j. Again, for any integer. So yeah, this whole stupid infinite family. Now, listen, if it were up to me, I would forbid the use of negative radius. All right, because to me it adds very little to the discussion, and it sets a great cloud of at the start of this. I hate it. I hate it with a pure hatred. But it is standard material, and I need to cover it. Yeah, and also if you use Desmos, it allows it. All the standard computer packages allow a negative radius in polar graphing. So I have to deal. I can't help it. I have to allow it. However, if you use this formula right here, r equals the square root of x squared plus y squared, your radius is non-negative, right? So you're never going to get minus the square root of 5 if you use the square root of x squared plus y squared, right? So this is a geometric add-on. And when I say equivalent, what am I saying? I'm saying that geometrically they correspond to the same point. How do you judge that? You plug the polar coordinates into the the basic equations here, and see if they reach the same point or not. Yep.
In general, do negative radians become more useful, for some certain something?
I really think it's just a matter of.
They just exist.
I think it's just a matter of graphing for the most part for us. In terms of applications to physics, I don't know right offhand. Negative velocity? I don't think they're needed because I can describe everything with the positive r and the right choice of angle. So I'm not convinced. You'll have to you can try to convince me later, but okay. So let's go on here. So sorry, I always, any amount of time I spend on this issue, I always regret. But it does need to be done, so now it's been done. Let's go on with our lives. It will come up in your homework. It will come up in the graphing. I'm not saying it doesn't matter to the course. It does matter to the course. I sadly cannot. I'd have to, I'd have to convince the entire community of mathematics to stop doing what they're doing. I have no such power. I'm not the God Emperor of math. So. It's not been one of those for a while. Let's see here. And you know what happens when people try to replace existing notations and make a new notation?
Execution?
No, not execution. What happens is the old notations persist, and they've just added yet another notation. This has happened many times. there were a bunch of French mathematicians who were publishing under a pseudonym called the Bourbaki. They were trying to do this. And they, I don't know, it was like pretty famous mathematicians, like a group of, I don't know, like 6 of them. It was a, I don't know how closely held secret it was for a while, but you know, they have all these, they're reworking all of the great things, and you know, you can, there's many volumes. It's like an encyclopedia of math in some sense, right? Written, this is from like the mid 20th century, but after all that was done, we now just have another notation. So, like, it didn't replace, it just come alongside. Okay, so graphing. Let's talk about example 3. Suppose you're up against x squared plus 2xy equals to 3. So this is a Cartesian equation, right? How do you find the corresponding polar form of this equation? What do you guys think? Yeah, exactly. We just plug in x equals r cosine theta, plug in x equals to y equals to r sine theta. What do we get? So we get r cosine theta quantity squared, right? Plus 2 r cosine theta times r sine theta equals to 3. And if you want to be pedantic, you could just be like, okay, I'm done. That's a polar equation. You wouldn't be wrong, right? And that may be about as good as we can do, actually. I don't think I can really appreciably simplify this much more. Well, oh, it is r squared. I can factor out r squared, cosine squared theta plus 2 sine theta cosine theta, yeah, equals to 3. And so this gives me r is equal to plus or minus the square root of 3 divided by the square root of cosine squared theta plus 2 sine theta cosine theta. Of course, the 2 sine theta cosine theta, you might want me to simplify to sine 2 theta. You could do that. It's not required or anything. But there you go. Listen, up here, polar equation. Down here, polar graph. What's a polar graph? A polar graph is when you write, it's actually, I'm still lying to you. So, sorry. I'm missing a letter. Because it's plus and minus, right? So it's not a single polar graph. You're looking at a pair of them. But if you can write r as a function of theta to describe your curve, this is called a polar graph. All right? Ha-ha! You will not escape me. Let's see here. Example 4. You could have, x squared plus y squared is equal to 4. Let's find the polar equation and or polar graph if we can, right? What is it? What's x? Well, we know x squared plus y squared is r squared. I suggest this is something you commit to memory. If at any point in this material you find yourself plugging in x and y in order to see that x squared plus y squared is equal to r squared, you're doing it wrong. You should know this. Like, you don't have to keep, you do that once, twice, maybe 3 times. Get it into your system. Cosine squared plus sine squared is 1. I know what's going to happen here. This is r squared. You're like, you haven't even worked out the details once today. That is true. I'm trying to model for you the behavior. So r squared is equal to 4. So that's the polar equation, right? And then what? Yeah, so, and then here's where that issue comes up. We could do r is equal to plus or minus 2. Like, algebraically, they're both allowed, right? So if you put r equals minus 2, you're using the silly number 2 option for the angles, right? So like, the angle is diametrically opposed to what your natural intuition says for the angle if you say r is equal to minus 2. But but we could just as well put r equals to 2, right? No loss of generality here, because r equals minus 2 and r equals 2, those are the same circle, right? R equals minus 2 is just the stupidly annoying angle described circle, okay? Let me just call it that. Shall we do another? So what's the other direction? The other direction of things is, given a polar equation, convert it to the Cartesian equation. So let's do that. Example 5. What if we have, let's say, oh, I don't know, r is equal to 2 sine theta. Now, there are different ways to go about this. The one is just to directly plug in the square root, and, well, if you do that, what happens? The sine theta, I mean, see, here's what's not, let me show you what not to do. Maybe that's helpful. Don't do this. This is what not to do. Right? It's of limited applicability because inverse tangent only gives you the angle where? You've just limited your scope, right? That's only good for angle, that's only good for quadrants 1 and 4, right? So that's a kind of, I've just, made twice the work, because if I do that, then I have to go back and, figure out what's the formula for theta over here, by the way. You could use this over here. You have theta is equal to pi plus inverse tangent of y over x, right? That is true, right? So, I'd have to do this, then I'd have to do sine of pi plus this for the other. You don't want to do that, right? So what's a better way? The better way is to make it look more like what you like. And so there's a simple thing to do here, which is just multiply by r. See, if we multiply by r, then everything's nice. Multiplying by r gives me r squared is equal to 2r sine theta. Which is ever so lovely, because now we know what we're looking at. We're looking at x squared plus y squared is equal to 2y. And there you go. That's a Cartesian equation for the curve. We can do better, though. What are we actually looking at here? How do you understand what this is? How about this? X squared plus y squared minus 2y is equal to 0, right? What do? Complete the square. That's right. So x squared plus parentheses y minus 1 quantity squared equals to 1. What is it? It's a circle. Where is it? It's centered where? X equals to, so center, 0, 1, radius, 1, right? So it's centered at 0, 1. Its radius is 1. So the circle we're looking at is this thing. Does this look like a circle to you? I mean, r equals 2 sine theta. Does that look like a circle to you? I mean, maybe it doesn't yet, right? But it is a circle. So the equation of a circle could look really different, right? Look at this, r equals 2 versus r equals 2 sine theta, both circles. A circle that's centered at the origin has a really simple polar equation, right? Just r equals to a constant. That should be unsurprising. Let's see here. I won't subject you to the algebra here, but I worked something out I thought it was amusing. So this is my example 6. So every so often I try to do something a little bit more general. So I thought, well, what would happen if I just take a circle of arbitrary center, right? X minus h squared plus y minus k quantity squared equals to r squared, right? So here we're looking at what? Circle at h comma k with center, with radius what? R. I'm assuming R is greater than 0. Okay. And what I did is I just plug in, you know, R cosine theta minus H quantity squared plus R sine theta minus K quantity squared equals to R squared. All right. And after about a half a page of algebra, I found this. R is equal to H cosine theta plus K sine theta plus or minus the square root of R squared minus parentheses H sine theta minus K cosine theta quantity squared. And I don't know, kind of amused me. Let me show you. Let's just try this out. Example 7. I have R equals 2 cosine theta. I'll do it two ways. I'll do it with my magical unsubstantiated formula. I have published the details for you here if you want to look at them. But let's, instead of using my, this is essentially a theorem, you know. What's theorem mean, by the way, guys? Theorem is essentially a word from a dead language that means, hey, look at this. Like, this is cool. That's all theorem means. But anyway, so if we multiply this by r, we get r squared is 2r cosine theta, which is x squared plus y squared equals to 2x. We do the same thing we just did on the other example. We complete the square. So we've got a circle centered at 1, 0 with radius 1. So that's r equals 2 cosine theta. It's fun, for me anyway, maybe not for you. No, it's fun for you too, to see if this works, right? So like, did I make a mistake in my half page of algebra? Maybe. I hope I didn't. Because if you look at this, this would be what? H is 2. Oh man. What's that? Go for the, oh, yeah, thank you. Thank you. I was like, this is hard. Oh, that's right. I should be looking at this, right? Oh, I see. Yeah, I think this is more interesting if you're going from the Cartesian to the polar, right? I'm trying to go the other way, which makes it not as interesting, but yeah, so this would say h equals to 1, k equals to 0, the radius is 1, and so this formula up here becomes r is equal to cosine theta, h cosine theta plus or minus what? Square root of 1 minus, what we got? Yeah, sine squared theta. So in other words, it is r is equal to cosine theta plus or minus cosine theta. So either r is equal to 0 or r is equal to 2 cosine theta. They're both there, right? The origin's part of the curve. Yep.
And you can tell that solution, example 6, also matches a geometric standpoint like vector.
Oh. Oh, really?
Like center at cosine and sine, and the distance formula like in the center.
Oh. So you just derived it geometrically? I'm interested.
You did.
I did?
That's the geometric definition.
This, you say this is, you see this geometrically?
Yeah, because that's the center of cosine
Huh.
and sine data. And then it's the distance formula away from
Huh.
by the
So this is the circle. You're saying I can see this formula from the circle? Or you're saying something else?
Yeah, because it's all the set points that are r distance away from h cosine theta k sin theta.
I mean, I agree that the equation of the circle is geometric. I'm asking about this equation down here. This is the one you see?
So
Oh.
the first part, that's the center. And then you add
That's the first part's the center?
the h cosine theta k sin theta. That's the center of the circle. And then you add a distance.
I'll have to think about it. Okay, so let's go on here. So, I mean, this is a relatively small part of this material, right? But this is something that's necessary. Well, actually, this is a pretty, examples 3, 4, 5, 6 to a lesser extent, 7. These are important because we have to learn how to take a given word problem and translate into polar coordinates, right? The other thing, past this, we need to talk about polar graphing. So let me do that. Sam, I'll talk to you about it after class. So polar graphing, ooh, I don't want to erase too much here. Show you how this goes. So example 8, what I do, 2 cosine theta, what's that look like? Looks like this, right? Whee! So it's at 2. So here I'm plotting r versus theta. This is what I do. This angle here is pi over 2, right? This angle here is 3 pi over 2, right? And it goes back. Like that, right? Back here is minus pi over 2. So step number 1, graph your, so given a, words. What I'm trying to explain to you right now is if you're given a polar graph, all right, in other words, r equals to a function of theta, how do you graph it, the corresponding curve in the Cartesian plane? So I advocate a 2-step process. Step number 1, you just graph, you know, basically look at the graph of f of theta, right? So here, you know, you've got f of theta is 2 cosine theta. I want to look at, because we already just worked it out, right? So I know the answer. I want to reproduce this answer from a graphical perspective rather than an algebraic perspective, okay? That's what I'm after. So there's my graph of f of theta. Fine. Now, I just have to geometrically track what's going on here. So down here, I'm going to put x and y. They don't have to be one over the other. They can be side by side. It doesn't matter. The point is you have to track. So let me just make some labels. Like here, let's call this A. What does that mean geometrically? I've got what? I've got r equals to 2, theta equals to 0. Where is that in the Cartesian plane? This is this point. All right? Let's think through this. When I get to pi over 2, right? That's B, right? Maybe I should do this point right here. Let me do this point right here, B. So there, I've got r equals to like a 1, maybe. And I guess if I'm at 1, I'm at like pi over... What do you... Cosine of... what is a half? Cosine of 60 degrees, right? So at like 60 degrees, I'm at 1. So it's something like 60 degrees, I'm at 1. So that's half of this. So it's like here-ish. Now, when I get here to C, I'm at radius 0, right? So at pi over 2, I'm at the origin. Let's see here. Now, this point right here, what's this? Let me do this one here. So let's say this is D. So D, I'm imagining D is r equals to minus 1, and that angle is what? 90 degrees plus another 60 degrees to get to minus a half. So I really should draw it more like here-ish. So what's 60 plus 1? Golly, what's that, 150? 90 plus 60, 150, right? And so this is where that annoying negative radius stuff, we can't avoid it. See, because when you're at 150 is over here, right? So you've got r equals minus 1 at 150, which means you're actually where? Over here, right? And if you keep picking some more points, right, you should be able to see that what you're doing is making that circle. And you really only need to study one, like one lobe, if you will, of the cosine, and you get the whole circle. If you go further out in the cosine graph, you're just going to keep duplicating. Let me do another example, which is more complicated, but that'll probably make it more, I would say, followable. You can follow it better, maybe. It saddens me to have to erase this, but I must. What's the other thing we should be doing with all this? Understanding calculus. Well, there's no calculus here yet, is there? We have to do the underlying algebra before we can get to the calculus, right? But I would say, in terms of graphing polar coordinates, goodness gracious, you really should get out the Desmos or whatever and use it, right? Check your answers, because this kind of graphing is challenging, I think. Example 9. Let's try this one out. Let's try to graph r is equal to 1 plus the sine of, oh, I don't know, 2 theta. Let's see what happens here. I'm not sure what this is. I just made this up. So we're going to discover it together, okay? Dr. Dromby tells me, Professor Dromby tells me I shouldn't do this. I should only do book examples. I wouldn't get into trouble. She's probably right. She's probably right. But I'm still going to do it because I like to live dangerously. Let's see here. And also, I have a computer with Desmos, so if we really get stuck, then we'll get unstuck rather quickly. How do you graph sine of 2 theta? By the way, I think in degrees. I don't deny it. But I do calculus in radians. Just remember that. Yeah. You say that's kind of hypocritical, isn't it? It's like, well, you're not wrong. So this guy oscillates around the line y equals 1, right? It starts out at 0, right? And it does one of these deals. Not 0. It starts out at 1. I'm a dummy. It starts out at 1, and then it does its thing. All right, something like that. All right. Now, and it goes back to, okay, right? Whatever. I'm going to start it here. Question, oh, maybe I shouldn't. Maybe I should think about going back to here. Not think about it some more. Where is this point right here in terms of angle? So here I'm looking at, you know, R, this is the R axis, right? So let's process it. What's the period of sine of 2 theta? Is it 2 pi? No, it's what? It's pi, right? So this point right here is pi, right? Here you're at what? pi over 2, right? So here, what are we looking at? Yeah, 3 pi over 4. Okay, great. And this here, pi over 4, right? Over here, negative quarter pi. All right. Sounds right. So what I like to do with this kind of thing is to draw some rays. All right, so like what's going on here is, well, what maybe I should go back to, no, I should stay here. So this is where, I gotta find the words. Let's see here. So at, where is it 0? It's 0 at minus pi over 4, and it's also 0 at 3 pi over 4. Are those the same? Minus pi over 4, where's that? So minus pi over 4 is like down here, right? 3 pi over 4 is, oh, it's over here, isn't it? And let's see here, what's going on? So we've got radius 0. We're coming into radius 0 here. Radius 1 is where? This point right here, right? That's radius 1. So that's at angle 0, right? So let me label this point A. That corresponds to, let's say, this one, right? Then how about this point here, B? Where's that? Pi over 4, right? So it's twice as far out though, right? So like here. Then what? This angle pi over 2, let's call that point there C. So tracking back, it's 1 out, it's like here, right? Doesn't look like this is a circle. Yeah? Something else. And let's see here, what happens at 3 pi over 4, we're back to 0, right? And so if you add some more points, right? Like that. Then you're going to do what? You're going to kind of fill it out. They get closer to 0 as you get into here. So it's something like up to the limits of my artistry here at the moment. It's an egg. All right, let's continue. I feel like that's not the whole story, right? You're like, well, how do you know if it's the whole story or not? I don't know. You have to investigate, all right? So at pi, we've got what? Let me call that A, B, C. I'm going to call this D. All right. So at pi, we've got point D. That is over here. Yeah. And what's this guy up here? What angle is that? Oh, 5 pi over 4. So at 5 pi over 4, so it's diametrically opposed to B, right? And I think you can see what this is going to happen, right? So basically you're going to, it's like 2 eggs, isn't it? Something like that. And I think if we go on, right, if we go past this point, what's this point right here? That is 3 pi over 2? Yeah, 3 pi over 2. So that would be 3 pi over 2 is like, is that 3 pi over 2?
Oh, no, there's one in between this 3 pi over 2. Yes.
This is 3 pi over 2, right?
Yeah.
That's good. You're 7 pi over 4. Okay, I feel better. Okay, good. So because 7 pi over 4 is this guy, right? So you go 7 pi over 4, and then you're going to go all the way over here to 9 pi over 4. It's going to repeat the loop. Okay, that's it. That's it. This is the process to make a polar graph. Carefully graph r as a function of theta, and then you translate that into the xy. I would strongly advise not trying to graph this directly on the Cartesian plane. Unless it's like example 5 or example 7, in which case, in example 5 or example 7, if you're asked to graph example 5 or example 7, and you do that laborious graph, the polar graph, then translate to the Cartesian, you're wasting your time. These can be graphed in 2 minutes because it's algebra. All you have to do is recognize circle. I can graph a circle, right? You don't need this whole nonsense. Well, it's not nonsense. It's the technique. All right. And let me. Oh man, we're gonna. I got it. All right. I just wanted to grab. I don't know what that thing is. I want to see what it is. You know. Let's see here. Oh, well, I guess you have to plug it in, huh? You're right, though. I do want to get back to calculus. Better to take our time here and finish the graphing today than to hurry through it and then still have to keep going back to it. You know? Let's see here. R equals to, what was it? Oh, I should do this one first. 1 plus 2 sine theta. Oh, sine of 2 theta. Woohoo! Hey. We did it. There it is, right? Oh, by the way, what's the Cartesian equation to this? That I'm gonna have to think about a little bit, but I would. So this is actually kind of challenging to find the Cartesian equation, right? This is r squared equals to, well, r cubed. Let's say r cubed is equal to r squared plus r squared times sine theta cosine theta over 2, also known as the cube root, well, excuse me, x squared plus y squared to the 3/2 power equals to x squared plus y squared plus 1/2 xy. So there you go. That's the Cartesian equation of this thing. Let's see if I'm right. Ah! What the? What the? What? Yeah. I said arrow. Take that. Yeah.
Is it?
Uh-oh. Oh, you're right. Thank you. Yep. You found it before I found it.